Hello, fellow students. Today we are going to answer a couple of students' questions. So stick around and enjoy yourselves. Okay, I'm going to share the Blackboard. And here we go with the questions. So the first question is, in the accessibility matrix, why a vertex is accessible from itself, right? So when we calculate this matrix, we always put ones on the diagonal, right? And it's easy to understand why, how we calculate the other positions, right? For instance, here, you can see how the vertex number 5 is accessible from 1 in this graph, right? We have the edge E that goes from 1 to 5. So we put a 1 in this position, right, on the accessibility matrix. But why do we put ones in the diagonal, right? Remember that this matrix tells is if a vertex is accessible from other one, right? So in the first row, we have the vertex that are accessible from 1. In the second row, we have the vertices that are accessible from 2, and so on. Right, okay, so coming back to the original question, in this case, you can see how there is a loop on the vertex 1, so that could explain this one. But as you can see, we have ones on all the other positions, even if we don't have loops on 2, 4, and 5. So to understand this, we need to go to the definition of path, right? So a path in a graph D is a succession of vertices and edges, right? Something like this. We start in the vertex 0, then we get the first edge that must connect the vertex 0 with the vertex 1. Then we have the second edge that must connect B1 with B2, and so on, right? Until we reach the last edge, we call it A sub n, and the last vertex, right? That we call B sub n. So now the point is that the length of the path, which is n, must be equal or higher than 0, right? Where n is the length of the path. So that means that if we have only one vertex in the path, we have a path of length 0, right? But it is a path indeed, because it meets the criteria to be a path according to the definition. And then the second point is, okay, so this was the definition of path. The second point is the definition of accessibility, right? So a vertex is accessible from other one, let's call it U, if, only if, it exists a path from U to B. Right? So in this case, you can see how a vertex is always accessible from itself, right? Because there is a path of length 0 from a vertex to itself, right? Even if there is no loop, a vertex is always accessible from itself. It is the same concept as, imagine if you were in the safe lock of a bank, right? You are inside of the lock. The lock is accessible from itself, right? You don't have to do anything to arrive there or to enter there because you are already inside. Okay, so let's go to, that's the answer to the first question. Let's go to the second question, which is why the order doesn't matter when we multiply accessibility matrices. Right, so for instance, when we are calculating M3, the accessibility matrix of order 3, right, so this is the answer to the second question. We can do it like this, right? We can multiply M1 by M2 or we can multiply M2 by M1. Right, it doesn't matter here. You can do it both ways. And you have these matrices here calculated for this graph. Now the question is why it doesn't matter, right? Because in general, matrices, the multiplication of matrices doesn't meet the commutative property, right? So if we were not talking about accessibility matrix, this changing the order of the matrices in the multiplication can lead to different results, right? But here it is not the case. Here it doesn't matter the order. It doesn't matter if we multiply one or the other. Well, the reason to understand this is you need to understand what these matrices mean, right? The accessibility matrix of order 1 contains all the paths that exist of length 1 from one vertex to other. So for instance, here we have a path of length 1 from 1 to 5. We have a path of length 1 from 2 to 1, right? So we put a 1 in the position 2, 1 of the matrix. For the matrix, accessibility matrix of order 2, it happens the same here, right? We can have a path of length 2 from 1 to 1, right? If we go 2 times through the edge A, we can have a path of length 2 from 1 to 2, right? If we go through E and then through D, for instance. So this is how we calculate these matrices. But when we multiply these matrices, we are, let's say, concatenating these paths, right? So to calculate the accessibility matrix of order 3, we are concatenating the paths of length 1 with the paths of length 2. So in this case, it doesn't matter the order, right? Because we can concatenate all the paths of length 1 with all the paths of length 2, or all the paths of length 2 with all the paths of length 1, right? And we will always arrive to the paths of length 3. If you want to think about it, right, let's take another imaginary graph, okay, with paths of length 3, right? So let's imagine that it is something like this, right? So if we want to calculate all the paths from U to B, we can do it in 2 different ways. Okay, let me make a copy of this graph. Right, so we have 2 options. We can say, okay, in M1, right, we have all the paths of length 1, and in M2, we have all the paths of length 2. So if we concatenate these paths, right, we arrive to all the paths of length 3 from U to B. But we can do it the other way around, right? We can have M2, right? All the paths of length 2, and then we can concatenate M1, right? All the paths of length 1. So this is what we are doing when we are doing the Boolean multiplication of these matrices, right? We are just concatenating the paths. So for instance, here, when we want to calculate the position 1, 2 of M3, right? This can be equals to the first row of M1 multiplied by the second column of M2, right? So it could be the first row of M1 by the second column of M2, which is a 1, or it could be calculated as the first row of M2 by the second column of M1, right? In this case, the first row of M2 by the second column of M1, right? So we are just calculating this path of length 3 in 2 different ways, but the result at the end is the same. Okay, and that's the answer to the second question. And the third question is, when we have a loop in a vertex, do we add 1 or 2 in the corresponding position of the adjacency matrix, right? So for instance, here we have a loop in the vertex 1, and we are adding only 1 in the position 1, 1 of the adjacency matrix. Usually, if we have two edges on this matrix, we have the value 2 to that position. But in the case of the loop, it's a bit confusing, right? Because you could say, yeah, okay, this is only one edge, but it is, I mean, the endpoints of this edge are the vertex 1, right? And in fact, it is adding 2 to the degree of this vertex. Well, it depends on the convention that you use, okay? So some authors add 2 to the position of the adjacency matrix when you have a loop, and other authors add 1, right? Depending on the book that you read and depending on the convention. In our case, we have the convention of adding 1, right? But depending on who you work with or who you read, you can add 1 or 2, right? So I would say that it's better if we stick to the convention that we have, but don't forget that if you work in other place, they can have a different convention. So you need to adapt yourself to the place where you are working on. Okay, so thank you very much. I will stop sharing the screen now. Thank you for joining me today on this lecture answering questions from students. If you have any other question, you can contact me. If you have any doubt, please don't hesitate to ask in the comments or to contact me with your doubt, and I will try to answer. So thank you very much for watching me today, and I will see you around in the next lectures. Bye-bye.